Take a look at 97J. This is one that is a trigonometric substitution problem. It's the integral of the square root of 9x squared plus 4. It looks fairly innocent. Again, notice there's no form of general substitution that will work. I can't just let u be 9x squared plus 4, because then my du is going to be 18x dx, and there's no 18x, or more importantly, there's no x being multiplied. If there was an x outside of this square root, that would be a simple substitution. Also, please do not say that the square root of 9x squared plus 4 is 3x plus 2. People incorrectly assume that the square root of a squared plus b squared is equal to a plus b, and that is incorrect. So you've got to work on your algebra as we're learning calculus. Got to remember how to deal with situations that look tempting but are obviously incorrect. If you square a plus b, you do not get a squared plus b squared. Okay. If you have any questions about that, please see me. Okay. With those general comments, let's see how to proceed. Now, typically, we are looking at something like x squared, but here we have 9x squared. Notice that's equal to 3x quantity squared. And so I could do a simple substitution where I let u be 3x. My du would be 3 dx. I'd have a 1/3 out here. I'd get u squared plus 4. But I'm going to do this just treating the 3x as the thing we want to assign. In this case, notice it's plus, so I'm going to use 3x is a tangent theta. And what's the value of a? Well, there's a squared, which is 4, so a must be 2. So I'm going to use 3x equals 2 tangent theta. Okay, so I'm just going to replace 3x with 2 tangent theta. Now, if I divide both sides by 3, I get x is 2/3 tangent theta. Okay. Later on, I want to know what tangent theta is actually equal to. So obviously, if I divide this equation instead by 2, I get tangent theta is 3x divided by 2, or 3/2 x. Okay, with the x, I do need my dx, right? What's the derivative of tangent? It's secant squared. So dx is 2/3 secant squared theta d theta. Okay, so now we replace the integral. It becomes, oh, sorry, before we do that, we got to figure out what is the square root of 9x squared plus 4. Some of you will know immediately what it is, just because you do these things over and over and it becomes apparent. But always check. I plug in for x. Of course, x is 2/3 tangent theta, so x squared would be 2/3 squared is 4/9 tangent theta squared. Okay, plug that in for x squared. Now the 9 times 4/9 is just 4 tangent squared theta plus 4. Factor out that 4, and in fact pull it out as a factor of the square root of 4, right? Pull that all the way out, and I'm left with the square root of tangent squared theta plus 1. Of course, the square root of 4 is 2, but with the Pythagorean identity, tangent squared theta plus 1 is equal to secant squared theta. And now I know I've chosen correctly, because the square root of secant squared theta is just secant theta. And then I've got the 2 here, so I get 2 secant theta. So, if this came out to be, something, if I couldn't get this as being a perfect square under the radical, it gets me nowhere. That's the whole point, of doing the trig substitution, is to get rid of this radical, this square root. And it's gone. It's just 2 secant theta. So now I can rewrite, our integral becomes the square root of 9x squared plus 4, that quantity becomes just 2 secant theta. And don't forget the dx. A lot of people, I notice when you're writing your integrals, will just leave off the dx like it doesn't matter. And it does, especially now, because the dx is not something just to be left off. It's actually 2/3 secant squared theta d theta. So I've got to copy that down. Okay, so there's my integral. I can now clean it up. 2 times 2/3 is 4/3. I'll pull that up. I'll pull that out rather as a constant multiple. Secant theta times secant squared theta gives me secant cubed theta. Now that one, I would not expect you to memorize or know. We do have our trig table, which gives us this formula for, powers of secant. It's number 12 in our trig integral table in the book. So with m is equal to 3 in this case, I've went ahead and just wrote out the whole integral form. And so I've got 4/3, and then plug in m is 3. I get 1, 3 minus 1 is 2, 1/2 tangent theta, of course, in this case, secant of 3 minus 2 is 1 secant to the first theta, plus 3 minus 2 is 1, 3 minus 1 is 2, so 1/2 integral secant of 3 minus 2 is 1 secant to the first power theta d theta. Okay. And then I can integrate secant theta. Some of you know it's the natural log of absolute value secant theta plus tangent theta. It's number 11 on that same trig table. I distribute the 4/3 through. 4/3 times 1/2. The 2 goes into 4 twice. I get 2/3. And make sure you distribute that through. So 4/3 times 1/2 gives me the 2/3 here. So here's my answer in terms of theta. I need to go back to the original variable x, and that's where, I'm going to, use the fact that tangent theta is 3x divided by 2. So I know what tangent theta is. I actually know what secant theta is. If you think about this equation right here, you can divide by 2, right? But, sometimes we need to draw the right triangle, and I'll do that since tangent theta is 3x over 2. That's opposite over adjacent. Here's my right triangle with my acute angle theta. Opposite side is 3x, adjacent side is 2. By the Pythagorean theorem, the sum of the squares of the two sides, right, is the square of the hypotenuse. So if I sum the squares of the two sides and take the square root, I get the hypotenuse. So I get squaring 3x, I get 9x squared, squaring 2, I get 4, add them, take the square root. There's the hypotenuse from the Pythagorean theorem. Now secant is the hypotenuse over the adjacent. 9 square root of 9x squared plus 4 divided by 2. So I'm simply going to replace tangent theta with the 3x divided by 2, secant theta with that, and same thing here and here. Right. Now I can clean this up a little bit. The 3's cancel, 2's cancel. I just have x times the square root of 9x squared plus 4 over 2. And then here, notice these two have a common denominator, so I can combine them as one fraction. Okay. Now you think that you would say, well, we could just stop right there and we have our final result. Well, if you'll look at my answer, it looks a little bit different. First of all, this first thing, I rewrite this first thing here as this. I hope everyone sees that dividing by 2 is the same as multiplying by half, so that's obviously the same. But then something's different. If you look at my answer, it's like I have everything the same except I don't have this divide over 2. I just have that in the numerator over 1 essentially. What happened to that 2? Okay, well, there's a property of logarithms, right, that says the natural log of a quotient, right, if I take the natural log of a divided by b, that is equal to the natural log of a minus the natural log of b. That's a property of logarithms. And so that's the tricky thing with logarithmic expressions, especially when we're looking at antiderivatives. We sometimes apply that to make the function simpler. So I'm factoring out the 2/3 for a moment. Natural log of a over b. So it's the natural log of the top, which is, of course, the top is the absolute value of all that stuff, minus the natural log of the bottom, which is the absolute value of 2. Of course, the absolute value of 2 is just 2. Okay, and we get this. But now, what is the natural log of 2? Well, it's just a constant. If I distribute the 2/3 back through, okay, what is 2/3 times the natural log of 2? It's a constant. It's a constant. So what we will do is we will absorb that constant into this general constant. And what do we have? A constant, right? It's the c can be anything. And so I can combine that natural log of 2, that really negative 2/3 natural log of 2 into that constant, and I get this new constant c. So this c right here would not be the original equal to the original c, but it would be this original c and this negative minus the 2/3 natural log of 2. So all we're left with is the 2/3 natural log of all this stuff. Of course, that first term is not affected. And this is what we have as our answer. And so that's how we get that result. So if you were wondering, you got to this point right here, and we're wondering what happened to that 2. Well, they're really equivalent expressions. In other words, if I were to graph this function here, where I have everything over 2 here, and graph this function without being over 2, what I would see is the graph of one function. Now this is not what the graph of the functions look like, but the graph of one function would look like this, whereas the graph of the other function would look like this. So that basically what's happening is they're a shift up or down from each other. There's a fixed shift, and that means they just differ by a constant. So both of these functions would be antiderivatives, right? Anytime we're talking about an antiderivative, we're talking about a family of functions, right? They all differ by a constant. So as far as a test goes, and if you were to get to this stage up here and did not proceed to this stage here, I would be completely fine with that, result. You would really have shown, if you got to this point, that you understand the trig substitution. But again, just to see, important how we can simplify things. It's very important, especially if we're going to use results in other situations. And so I want you to be aware of that, especially as you're checking your homework. Okay, so hope that this helps explain this one.